We are students of Mapua University and we are here to discuss about retaining walls, specifically cantilever retaining walls. But first, what is a retaining wall? A retaining wall is a structure designed and constructed to resist the lateral pressure of soil when there is a desired change in ground elevation that exceeds the angle of repose of the soil. The most important consideration in proper design and installation of retaining walls is to recognize and counteract the tendency of the retained material to move downslope due to gravity. This creates a lateral earth pressure behind the wall, which depends on the angle of internal friction and cohesive strength of the retained material, as well as the direction and magnitude of movement the retaining structure undergoes. Lateral earth pressures are zero at the top of the wall and increases proportionally to a maximum value at the lowest depth. Earth pressures will push the wall forward or overturn it if not properly addressed. Also, groundwater behind the wall that is not dissipated by a drainage system causes a hydrostatic pressure on the wall. The total pressure or thrust may be assumed to act one-third from the lowest depth or for length stretches of uniform height. Unless the wall is designed to retain water, it is important to have proper drainage behind the wall in order to limit the pressure to the wall's design value. Drainage materials will reduce or eliminate the hydrostatic pressure and improve the stability of the material behind the wall. Dry stone retaining walls are normally self-draining. As an example, the National Building Code of the Philippines requires retaining walls to be designed to ensure stability against overturning and sliding, excessive foundation pressure, and water uplift. That they have to be designed for a safety factor of 1.5 against lateral sliding and 2.0 in overturning.
There are four major types of retaining walls. First, the gravity-poured concrete retaining walls. Gravity retaining walls depend on their own weight and any soil resting on the concrete in resisting lateral earth forces. They are generally economical up to 10 feet in height for cast concrete structures, usually are sufficiently massive to be unreinforced. Monolithic cast walls are generally formed on site. Second, the semi-gravity retaining walls. A specialized form of gravity walls is a semi-gravity retaining wall. These have some tension reinforcing steel included so as to minimize the thickness of the wall without requiring extensive reinforcement. They are a blend of the gravity wall and the cantilever wall designs. Third, the counterfort retaining walls. Counterfort retaining walls are similar to cantilever walls, except they have thin vertical concrete webs at regular intervals along the backside of the wall. These webs are known as counterforts. The third one is the cantilever retaining walls, where we will focus on this type of retaining walls. Cantilever retaining walls are constructed of reinforced concrete. They consist of a relatively thin stem and a base slab. The base is also divided into two parts, the heel and toe. The heel is the part of the base under the backfill. The toe is the other part of the base. And cantilever retaining walls use much less concrete than monolithic gravity walls, but require more design and careful construction. Generally economical up to about 25 feet in height and can be precast in a factory or formed on site.
There are 5 types of modes of failure. First, sliding failure. Second, overturning failure. Third is bearing capacity failure. Fourth is shallow shear failure. And the fifth one is deep shear failure. First is sliding failure. What is sliding failure? Sliding failure is nothing but sliding of wall away from the backfill when there is shearing failure at the base of the wall. The factor of safety against sliding is where mu is the coefficient of friction, or we can solve it by tangent sigma, and RV and RH is vertical and horizontal components of the resultant R of weight of wall and earth pressure, which should be less than 1.5. Second is overturning failure. What is overturning failure? Overturning failure is rotation of wall about its toe due to exceeding of moment caused by due to overturning forces to resisting forces. The factor of safety against overturning is given by where the summation of MR is equal to the summation of resisting moment about toe, and the summation of MO is the sum of overturning moment about the toe, which should be less than 1.5 to 2.0.
The third one is the bearing capacity failure. The pressure exerted by the resultant vertical force at toe of wall must not exceed the allowable bearing capacity of the soil. The factor of safety against bearing failure is equals to the allowable bearing pressure over the maximum pressure, and the factor of safety should be less than 3. The fourth type is the shallow shear failure. This type of failure occurs along a cylindrical surface ABC passing through the heel of the retaining wall as shown in the figure. The failure takes place because of the excessive shear stresses along the cylindrical surface within the soil mass. The factor of safety against horizontal sliding is lower than that for shallow shear failure. However, the factor of safety against sliding is greater than 1.5. Shallow shear failure is not likely to occur. Lastly, fifth, deep shear failure. This type of slope failure occurs along a cylindrical surface ABC as shown in the figure. When there is a weak layer of soil under the wall at a depth of about 1.5 times the height of the wall, the critical failure surface is found by trial and error method. For the backfills having slope less than 10 degrees, it has been seen that critical failure surface DEF passes through the edge of the heel slabs as shown in the figure. In this condition, possibly of excessive settlement should also be checked.
So good morning, I'm here to discuss about sample analysis of our calculation of an normal cantilever beam in which we will analyze its safety. So we will check its safety for overturning and for its sliding. So we have a normal cantilever beam here in which we have 8 meters in depth and 5 meters in width. So we have different types of soil in different parts of the cantilever. So in this part, we have a granular backfill in which we have an angle of repose of 30 degrees and a unit weight of 18 kilonewton per meter cube. In the base part, we have a medium dense silty sand in which we have a unit weight of 20 kilonewton per meter cube and the angle of repose of 32 degrees. So in this field, we have also another type in which we have a unit weight of 20 kilonewton per meter cube and it doesn't have an angle of repose. So first, we will have computation on how to get the coefficient for computing the active soil pressure, in which we'll use the Rankine's formula, which is equal to 1 minus sine theta over 1 plus sine theta. So in here, we will substitute the angle of repose, which is 30 degrees, for the surcharge, in which we will compute its active soil pressure. So once we substitute the 30 degrees here, we got a value of 1/3 here. Once we get the value of 1/3, we will now compute for the active soil pressure, which is equal to the coefficient times gamma times the height in which the soil pressure will start. So now we will compute for the active soil pressure. So first is we will compute the active soil pressure by the surcharge, in which we have a Q of 30 kPa. So first is we will get the 30 kPa times 1/3, which is the coefficient in which we will compute for the active pressure, which we will have a value of 10 kPa. So next is the active soil pressure, in which we will consider also the soil of the whole figure. So in here, we have 30 plus 18, in which 30 we got from the surcharge, and then 18 is from the unit weight of the soil here. So we will multiply it by 8, since we will consider the whole soil which is in here. So we had an active soil pressure of 58 kPa. So in here, we have a free body diagram of our resisting forces versus our overturning forces. So for our resisting forces, we have different vertical forces, which is downwards, which acts as a self-weight of our cantilever wall, and also the soil pressure acting on the cantilever wall. Another is our overturning forces, which we got from our active soil pressures that is acting on the cantilever wall, in which we have H1 and H2, which is a horizontal force acting on the cantilever wall. So next is we will calculate all of the moments of the vectors that is acting on the cantilever wall. So first is we will get its force first. So we will get force of V1, V2, V3, V4, and V5, in which we will get the force by multiplying the area affected by the vector times its unit weight. So for the unit weight of concrete, which is the self-weight of the cantilever, we have 24. So for example, we have V1, which is 0.5 times 7, this is the 0.5 times 7 times the unit weight, which is 24, which is 24 here. So next is we will multiply it by the lever arm, in which we will take its moment about the toe. So once we got the force, we will multiply it by the lever arm, in which we will take a moment about its toe. So this is the reference point in the toe. So we had the 1.25 meters of lever arm, in which we got from the centroid of the area of V1, and then we have additional length of 1 meter here. There, 0.25. So we had the 1.25 meter here, in which we will now multiply the force by the arm to get its moment, which is 105 kilonewton per meter. So we will do that for all the vectors, in which we had a summation of moment of resisting forces of 1,855.75 kilonewton per meter. So next is we will calculate for the overturning moment. So we got the so for the overturning moment, we will also multiply the force by its arm. So in getting the force, we will get the force of vector H1, in which we have the vector acting upon here, in which we got 10 kPa as the active soil pressure from the surcharge of 30 kPa. So this 10 kPa is then multiplied by the total depth of the cantilever wall, in which we will get is equal to the area of this figure here. So 10 times 8 is equal to 80, and then we will get its lever arm, which is 4, which we got from the centroid of this figure also. So the centroid of this rectangular figure is equal to 1/2 times its total depth, in which 8 over 2 is equal to 4. So the same can be done in vector H2, in which we also got centroid of 8 over 3, which is 1/3 of the triangular figure here. So the total overturning moment we got is equal to 832 kilonewton per meter. So for the last part, we will now compute for the factor of safety of the cantilever beam, in which we will compute for the factor of safety for overturning and for the sliding. So for the factor of safety for overturning, we will have a summation of resisting moment over the summation of the overturning moment, in which we got from the previous calculation, which we have 1,855.75 kilonewton per meter over 832 kilonewton per meter, which is equal to 2.23, which is our factor of safety, in which for our factor of safety for overturning should not be greater than 1.5 to 2. So we have a value greater than 2, which is not safe, okay, for the overturning factor of safety. So in computing for the factor of safety for sliding, we have a formula of the summation of forces for resisting times the base friction, in which we have from the given value from previous, over the summation of forces for the overturning, in which we got from the previous calculation, we have the summation of forces for resisting is equal to 655.5 kilonewtons times 0.5, which is we got the given, which is the base friction, over 272, which is the summation of forces for overturning, in which we got 1.2 for the factor of safety, which is less than 1.5, which is safe for the factor of safety for sliding.
So here are the applications of the cantilever retaining wall. As you can see from the first picture, that the cantilever retaining wall is made up of concrete that is built along the edge of the road. As you can see, that is along with the cars, as shown on the picture. Okay, as shown on another picture, which is the cantilever retaining wall that is formed on the snow, which can be used to easily walk around on the other side of the road and can prevent avalanche. Here it is the precast retaining wall that is shown on the picture that is still on progress, that later it will be formed and then the soil will be poured that is behind it, which can use to prevent erosion.